I'm gonna talk about what we do at Kipu Quantum, and I'm gonna talk about who Kipu Quantum is. We are a relatively young company. We're 1 year old, and we have been trying to tackle a challenge based on using quantum computers, current quantum computers, for industry relevant application, which is really a challenging task. So, yeah, that's me. Looks like me at least. So, as you see, I'm the lead developer there at Kipu Quantum. And essentially, Kipu Quantum is working for some large organizations that have already started their journey in quantum computing. They already tested some of the, let's say, canonical approaches, some of the state-of-the-art approaches, and our approach to them is that you can do a little bit better than what they have tested. In particular, if you embrace the hardware as it is, not abstracting too much the application from the actual hardware. So most of the use cases that we have been working until now are related to chemistry and combinatorial optimization type of problems, and this is also because of the technology that we are using at Kipu Quantum. It basically natively can be deployed in this type of use cases where you can pose your problem as the ground state of a given Hamiltonian, and that, I'm going to talk a little bit about that. So first of all, Kipu Quantum works with these, let's say, three main visions that are application specific. So whatever we do, any algorithm that we develop, it's dedicated to a specific application and tries to benefit from the nature and the nuances that each application may have in different industries for different use cases. And we do that using quantum computers, current quantum computers, market available quantum computers, so nothing quantum inspired. It's a big challenge when you try to take these applications into the actual devices, and you are limited somehow by what they can do. But if you squeeze all your knowledge into these specific features that each particular hardware vendor has, you can actually do some really interesting things. And the idea is that if we can combine these two, we can take some proof points that may not be industry scale, but they will be industry relevant. They help us design a roadmap, design a moment in the future, and ideally in the near future when they will be able to make the switch. So some specific business use cases may be able to benefit from this technology when we improve the hardware, when everything in the full stack improves, and they can actually make this switch. And the idea is to paint that picture, to know when they will be able to make that switch. So at Kipu Quantum, we try to cover the whole spectrum from the customers to the hardware. We partner with the main technologies right now, and we have partners in photons, in ion traps, cold atoms, and superconducting circuits. We do work with customers trying to understand what is the use case, how they pose it, how they frame it, and essentially help them bring it to the shape, the mathematical shape we need in order to leverage our technology, which is essentially a compression, a technology based in compressing the algorithms. And I'm gonna detail a little bit about that, but essentially we're trying to cover the whole spectrum. So we engage in projects with customers, but the idea is that if we find this path, let's say from a chemistry-related use case that benefits from our technology in a given specific hardware, the idea will be to build products in the future. Right now, we are mostly engaging into projects to really understand what are the challenges that our customers face. Regarding the compression technology, it's a different version. It's not a mainstream approach, and it's based on the algorithmic compression. So even before you have the circuit, you try to pose your problem so that it will get solved in the minimum amount of steps. And then, of course, you can digitize it to take it to hardware. In some cases, you can benefit of some of the analog blocks that the hardware already has and remove all your entangling gates, let's say, at logical level, and benefit from the actual analog entangling blocks that the hardware provides. And in some other cases, you can even go fully analog. So depending on the platform we will end up running, these are the three flavors we end up having our algorithms implemented at. And to give you an idea of what this is all about, essentially we take a concept like adiabatic quantum computing. One of the challenges we face when we try to implement this approach into real hardware is that in order to guarantee that you start with the solution to a simplistic problem and you little by little morph it, let's say, to the target problem, you have to make really small steps so that you can ensure that what you end up having is actually the solution to your problem. This means that if you do this evolution for a long period of time, you probably will exceed the qubit lifespan and end up having something that is more classical than quantum. And if you try to accelerate this approach, essentially you minimize the gap and you may have transitions that move your actual solution, the solution of the initial problem, to something that is not the solution of your target problem. So there has been many people working on this, how you can accelerate this, how you can improve this. And there is a really interesting paper, a seminal paper called Shortcuts to Adiabaticity, that explains some of these techniques that you can use. So one that we have used a lot and has proven to be beneficial for what we do is what it's called the counter-adiabatic protocols or counter-adiabatic driving. Essentially, you add that term that is called the adiabatic gauge potential, the A lambda term, and essentially that helps you control. So removes the non-adiabatic transitions, let's say from the ground state to excited states while you do the evolution, and that helps you accelerate the whole thing. And actually computing that thing is really complex, so it actually requires the same resources as solving the problem, so it's not pretty convenient. But there are many works approaching how you can approach this adiabatic gauge potential, and this is a really interesting one, because you can actually decide the expansion. If you take L to infinity, essentially you're computing the adiabatic gauge potential, the exact adiabatic gauge potential, but you can decide and see if the first order expansion already provides enough acceleration and enough enhancement of your ground state, your solution to your problem, so that you can actually run it on hardware. And this is what Kipu brings to the table, basically the expertise on knowing when and how you need to implement these approximations. So to put some numbers to this, I wanted to point out some of the, let's say, key points of this article that I'm referencing there, which we basically did a hardware implementation for a 20 portfolio optimization type of problem. We took the adiabatic approach, basically evolved it for a long period of time, or long enough period of time, and then we implemented the counter-adiabatic approach, which is this CQO that you see in blue there. We get a distribution that the approximation ratio of this distribution is closer to the ground state, but the interesting thing is that actually you have 200 less entangling gates needed for that specific distribution. So if you are accelerating the whole process, when you digitize it, when you take it into trotter steps and you make gates out of it, actually you need just 64 entangling gates in comparison with 12,000 that you would need for the adiabatic approach. So that's basically the core idea and why Kipu was founded. And there could be some criticism saying that if these type of problems, you don't approach them in current status of the hardware, you don't approach them with this, you use variational techniques. Fair enough, we also tried this. So there are two main ways to construct your ansatz. It could be application specific, like UAOA, or it could be hardware specific, like hardware efficient ansatz. We made the same thing here. We decided to go with both application specific and hardware specific. We create a city-inspired ansatz, essentially adding counter-adiabatic terms. So if you look at quantum, at QAOA, which is basically a trotterization of the annealing, the digital version of the adiabatic quantum computing, and you free the parameters, so your alpha and your beta, essentially by adding these city terms, this third block that has additional parameters, you can train it. And even though you are adding one more parameter or one more layer, what we say is that essentially one of these ansatz is equivalent to five repetitions, 5 layers of QAOA. So it seems to capture more, because in QAOA, in a single layer, you will need to repeat it several times so that it converges to the ground state you want to achieve. And in this case, you can see that it can be done in a single step with this variational approach of counter-adiabatic protocols. So this is the core idea, the technology we're trying to implement with our customers. And when you have these statements that you can accelerate and you can make things fit into current hardware, they don't believe you. It's amazing. They challenge you first with toy examples. They have been playing with these examples on different types of machines with different types of approaches, and they want to challenge you. If you can actually prove me that this works for traveling salesperson problem, then I will let you play with the big problems, the job shop scheduling, the workforce shift planning, whatever they have. So this was when we started working with this company, and you can see it's a little bit biased towards Germany, but it works also in other geographies. So basically, we started working with this TSP in different some problems they already have posed, and they asked us to solve it. So the example that I'm showing here is basically 9 qubits, so 3 cities in this case, traveling salesperson problem. 9 qubits, we went with the vanilla approach, and we see that there are 6 peaks in this vanilla approach, so what we get from the simulation. At this level, you can still brute force and confirm or validate that there are actually 6 potential solutions. The main challenge, and actually that's one of the issues they had when they went to hardware, is that basically the success probability of your solutions gets divided into, in these 6 potential solutions. So when you go to hardware, it may be challenging that you can retrieve something out of it. So we tweaked the algorithm, we made it specific for this application, and essentially we made a variational approach that selects one of those solutions, we don't know which one, but selects one of those, and basically trains over it, making it so that we can select one of these 6 potential solutions with a larger success probability, 80%. They were actually, they wanted us to do it in IBM hardware, so that's what we did. And basically, after the error mitigation and error suppression techniques that were applied, we got a 20% success probability on hardware, which essentially means that we can still recover the solution from it. So with this approach, they were happy with it, and we tried to scale it up to 16 qubits and 25 qubits actually. And I want to show one particular example that I think it's interesting. It's that this is the 16 qubit approach, and actually the gap, you see the decrease you see from the simulated result to the hardware, it's not as significant as with the smaller example, which is a little bit counterintuitive. So this is the direction in which we are still evolving and further compressing the approach so that we can benefit of those specific, like in this case, it was due to the number of zeros and ones that the solution that we fixated in had. But we are trying to take advantage of those so that we can maximize, and actually running on hardware, we can still retrieve meaningful results. And the idea, of course, is once that we have validated this strategy, make it work for the other combinatorial optimization problems they have. So essentially, these are the 3 lines we are following, finding these use cases that will fit into this similar strategy that we use for TSP, further improve the digital compression using these insights that we learned from these initial experiments, and of course, propose different platforms for solving combinatorial optimization problems, because there are platforms that fit better into this approach, and we are actually working with our partners or with our hardware platforms partners that in order to see which one would be the best approach for this. Of course, if you are not part of this partner ecosystem, feel free to reach out. If you are interested in these compression techniques, reach out. If you want to discuss something, reach out. So you have my QR code there. You can scan it, my email there, and thanks so much for attending.
All right, so we do have a few minutes for questions. Are there any questions for Iraitz? All right, if there are, oh, okay.
I might have missed this, but how big was the optimization problem? How many nodes in the system?
Yeah, for the TSP one that we solved, is essentially this 9 qubit problem. It's a 3 city problem. The 16 one was a 4 city problem, and the 25 one that we tested as well, it was a 5 city problem. So it's not industry scale, but the idea was to show that there was a strategy that we could use and scale it up.
Any other questions?
Thank you for the nice presentation. Do you approximate the counterdiabatic Hamiltonian or whole counterdiabatic Hamiltonian?
So let me go back to the slides. So essentially, the challenge is computing this A lambda term. If you need to exactly compute it, I mean, you have enough resources to actually solve the problem. So what we have done essentially is use in this case, the first order expansion, and that it's enough, at least for this case. So it's not complicated to compute it with this. At least with this approach, it's really simple. You can easily translate it to digital gates, to the gates in the hardware, and first order expansion is enough. There is also a challenge there defining what is the expansion. So how much time you need to spend computing this, so that it's efficient, let's say, and you maximize the success probability. So that's basically the secret sauce.
Okay, so do you think there's a balance between the number of terms from this and the complexity of the problem, as well as the number of entangler in the circuit? How do you think?
Yeah, it's tricky because when you work at this analog level, the expansion of the city terms doesn't represent an increase on the entangling gates. And actually, if you go with the analog approach, basically you can replace whatever chunks of entangling gates with just a single big block, big entangling block, and simplify that. So there is not a direct relation between the expansion of these terms and how the circuit ends up being in these three approaches that we are using: fully digital, digital analog, and fully analog. So it's a difficult question to answer. Okay.